on that by
from Adam Szczepaniak. He will talk about exploring hadron mass with exotics.
Thank you, Finko, and thanks the organizers for inviting me. Hope you can see the screen.
Yeah, we can see it.
Okay, great. I'll talk about recent work that we've done at JPAC on understanding production of exotics, in particular the exotic hybrid meson. But if I have a time, I'll also say a few words about the XYZ states. As I mentioned, this is work that we've done at JPAC. In particular, I'd like to thank Daniel and Vincent. Vincent, I'm sure everybody knows, Daniel is my PhD student at Indiana. They let me use some of their slides from the talks that they recently presented at the APS meeting earlier this week. So to understand hadron mass, obviously we need to understand what gluons do in QCD. Gluons are, as everybody of course appreciates, very peculiar. On one hand side, they confine color. On the other hand, they are also confine particles. So to distinguish these two characteristics of gluons, a gluon field is often practical to choose a physical gauge, light gun gauge, radiation gauge, to split interactions from particles, potentials from particles. And what you see here on the right-hand side is a lattice data on essentially what corresponds to a molecule in QCD. The top little instant here is the molecular potential in between sodium and chloride that emerges from integrating out the electronic degrees of freedom. The data here in the bigger plot corresponds to potential between heavy quarks after integrating out gluonic degrees of freedom. So data is from the lattice from 20-year-old calculations from Colin Morningstar and company. There have been a number of calculations done ever since after that. And the lowest line is the Cornell potential. And then you see the excited levels corresponding to states in which the gluon field is excited. So this, again, you can think of as the potential between quark and an anti-quark in various configurations. And to explain these potentials, again, one can think of that as I said, integrating out physical gluonic degrees of freedom. And the picture here in the bottom shows schematically how the potential gluons, which are depicted here as the vertical lines, are separated from the transverse gluons, the horizontal lines, which behave as particles, and the interactions between confined gluons and the potential, which again emerges from in the radiation gauge, leads to this particular ordering of the various surfaces. Now, the lines are above the data because this is, of course, a variation calculation. It's very difficult to do this exactly in QCD, obviously. So from this picture also emerges a sort of phenomenological interpretation of an interesting phenomenological interpretation of what the excited states now of dynamical hybrids, meaning with quarks no longer static, but moving together with the gluons looks like. So on the left, you see the normal quark anti-quark spectrum. This is from, again, just sort of a schematic here calculation, but it's an actual calculation from high spec, with corresponding to rather heavy pion mass of about 700 MeV. And in this calculation, you see these other multiplets of states with large overlap with gluonic operators. And the ordering of states in these multiplets can be explained in terms of these quasi-gluons with very particular quantum numbers, 1 plus minus, that gives in particular in the lowest orbital excitation, S waves give this lowest for states, including the exotic 1 minus plus quantum numbers. So again, this is just a path, a particular path towards understanding what gluons do, how they contribute to to the spectrum. Of course, historically, one of the first connection between confinement and data is being done through the observation of Regge trajectories, very linear Regge trajectories of both mesons and baryons, which again, if they were to rise linearly out of infinity, that would correspond to essentially a rigid string rotating between quark and an anti-quark. Here's just a few trajectories, baryonic trajectories, again showing this linear pattern on for both natural and unnatural parity states. Of course, these things will no longer cannot rise forever. States resonances decay. Eventually, higher masses and higher spins would start overlapping more and more with multi-quark and multi-gluon states and become essentially jet-like. So these trajectories, which eventually start to bend, and at some point they will saturate. But again, before this happens, somewhere in the lower mass region, you can argue that what maybe 2-3 body decays dominating the hadronic spectrum, how hadrons decay, and you can implement that and also compare calculate and compare with the data the imaginary path of trajectories, and that's shown in the right side. I'd like to say a few more words about reggelons, because I think this is the topic that, at least for to younger generation, is maybe not so well covered anymore, and I think it's an important aspect of understanding hadron dynamics and QCD confinement in particular. Of course, one of the aspects that I think is fairly familiar is that Regge phenomena are somehow related to description of energy of reactions at high energy, something that is related to the ability for one to factorize the fragmentation, for example, of the beam from the fragmentation of the target. And of course, this type of factorization essentially implies that whichever way this reaction proceeds must somehow correspond to an exchange of something, of an object with sort of particle-like characteristics that can be moved between different beam target configurations. And this particle-like characteristics, that's what characterizes a reggelon. So reggelon is, in a sense, an effective particle. So very crude introduction to what reggelons are. So here on you see a sketch of essentially hadron, quasi-hadron two-body process, two hadrons AB scattering into hadrons CD at high energies. The kinematics is such that, again, S is the Mandelstam variable representing the center of mass energy squared. T is the momentum transfer, Mandelstam variable representing momentum transfer. Interesting here in the kinematics, in the scattering angle is small, T is fixed, and S is large. So this corresponds certainly to the forward scattering region with little recall between, say, beam, the forward moving, the beam and the forward moving particle. At high energies, essentially, we can assume that the hadrons essentially interact as black disks, namely all essentially partial waves, which are less than some critical, essentially classical value that is determined by the momentum of the relative momentum between the hadrons and their size, are completely absorbed, and all the partial waves with angular momentum higher essentially are hadrons with these higher partial waves essentially scatter without interaction. So if you convert that into what the simple assumption, as I said, that all the lower partial waves are completely absorbed, which corresponds, of course, physically to inelastic scattering, that gives an amplitude which is written in terms of Mandelstam variables, grows with energy as 1 power of S, and is imaginary because all the absorption corresponds to imaginary partial waves. Now, what happens sort of when the disks interact at the edges here, the periphery? Well, that corresponds to, or that is measured through this low momentum transfer dependence. So that introduces dependence on momentum transfer. And here from the Mandelstam variable, one can convince, from the Mandelstam plane, one can convince oneself that if you go to high energies, then you're essentially sensitive to the lowest physics, lowest singularities that happen in the T-channel. So for example, you could think that the lowest possible mechanism in which these two disks can interact in the T-channel is exchange of low mass particles, for example, two pions. So that the lowest singularity will be determined by the location of the two pions. So the F would be dominated by that singularity. So this is sort of a naive picture of high energy scattering. Now, of course, what radiation does is when hadrons recoil, they have to radiate, and that corresponds to, instead of essentially being black disks of a finite size, something which grows with energy. Black disks become gray disks with the radius growing with energy. And now if we take this, take this rotation, we take this radiation and rotate by 90 degrees, we come to a picture in which the radiation from hadrons essentially starts being up this type of ladder exchanges. And that now starts indeed looking like a particle in the T-channel. So now interpreting this ladder exchange in terms of its spin, one sees that since these exchanges now occur in the T-channel at large scattering, one sees that the energy dependence is essentially determined by sort of an effective spin of these ladders. So the power of 1, which we had for this naive black disks, now becomes replaced by something which is effective, which depends on the momentum transfer, but still essentially has an interpretation of spin of that object. So this is what the reggelon is. Again, from this sort of heuristic interpretation, you see that indeed it looks like a particle. It factorizes between how it interacts with the two blobs and has a running spin. And for certain values of momentum transfer, that corresponds to this Regge trajectory alpha corresponding to integer numbers, that really becomes a particle. So as I said, reggelons are sort of like superparticles. They really are the effective degrees of freedom to describe high energy scattering. These trajectories for of course physical scattering in the S channel correspond to negative spin or lower spin. And again, if one then increases t going away from the forward limit, then one expects, for example, the various trajectories to interact with each other and eventually, for example, correspond to exchange of quarks. This is what's being done. What Stan showed many years ago, how the Regge trajectories saturate and correspond to quark exchange processes. So all this physics is encoded. And as I said, since the effective degrees of freedom representing scattering, then one can build an effective theory that enables one to go beyond the simple particle-like factorizable description of high energy processes, including interaction between reggelons, et cetera, and describe corrections to this leading factorized behavior as to power alpha. Now, if you go to the positive values of t, then indeed, whenever a trajectory crosses an integer number, then reggelon indeed becomes a real particle. So again, it's how the Regge trajectories behave is telling us much more than about the spectrum of QCD and what makes that spectrum than just looking at individual hadrons one by one. So indeed, the fact that the Regge trajectories keep on rising at least over a certain range of energies essentially gives us the connection between existence of rho meson and the high spin rho mesons. And radial excitations that correspond to trajectories which are called dotted trajectories that are shifted. Same with multi-quark states. Long time ago, again, was shown by Rossi and Veneziano how existence of things like tetraquarks and pentaquarks are connected to in the large NC limit to certain duality reactor processes involving baryon and anti-baryon scattering. So again, it would be interesting to think about what the XYZs are in the context of Regge trajectories. And of course, not all trajectories have to be linear. Again, if all these various states that we claim do not somehow fit into the traditional quark model classification may indeed represent different types of dynamics, just like the sigma meson we have shown some time ago has a quite different Regge trajectory, or appears on a quite different Regge trajectories than, for example, the rho meson. So here is again a little summary of for example, and classification of states of light mesons from the perspective of reggelons. What you see here on the table below the dashed line, these are the isovectors. Above the dashed line are the isoscalars. Again, on the right is as I said, the heavy pion isovector meson spectrum from the lattice simulations, and the 1- exotic meson that Gernot was already talking about. In principle, it lies on a trajectory with another exotic pi3, and the pi1 would be, in terms of the sort of microscopic quark gluon constituent models, will be part of this multiplet. Now, there's another interesting possibility here. The states in the D-wave multiplet, the 2-, for example, they do not have exotic quantum numbers. They are just coupling between quark and anti-quark spin 1 with orbital 2 units of orbital angular momentum, but they've never been seen. So what would be referred to as the ρ2 meson, as I said, never been seen. There's a possibility now of really having high statistics data on ρ3 from GluX, sorry, ρ2, not ρ3, decaying into, say, omega pi. So that's a possibility of looking for it. But then a lower member on its Regge trajectory would be the ρ0, which does indeed have exotic quantum numbers. So maybe the ρ2 isn't there because, again, it's connected with something which is exotic. The B1 and B3, the B1 is seen. This is, again, the normal P-wave meson. But then the B with even spins again correspond to exotic trajectories. Again, the have not been seen, and only B1 have been seen. So let me now move on to the exotic 1-. Say a few more words about that state. So again, we're all familiar with the data. There's been a lot of signatures of the 1- in the past from various diffractive, high diffraction experiments, mainly using pion beams. Here on the left, you see a plot from COMPASS in the 3 channel. This is the highest statistics experiment so far looking at the 1-. Now, the complication of the 3 of the pion diffraction and measurement in the 3 final state is the presence of this large contribution from, as I said, from pion diffraction, from pion exchange, which gives large background, in particular also large background projecting onto the P wave. And this is clearly seen in the COMPASS data, specifically low momentum transfer. The data indeed does seem to be mainly dominated by the so the green line, the green line is essentially the effect of diffraction. So you see the peak is mainly dominated by that. However, if you move to high momentum transfer, it is known that this process decreases, and the presence of the peak now may indeed indicate that that's primarily dominated by the exotic meson produced directly. This type of processes, again, were what motivated largely looking at these at pi 1- production using photon beams, again, but because of the different possibilities of, for example, using having charge exchange, charge pions that in principle could lead to yields which are for exotics which are as large as those of normal mesons like the A2. So instead of looking at the 3 it seems to be more efficient to look at the diffraction of pions into a 2 meson final state, particularly eta pi or eta prime pi, because the P wave in the system has exotic quantum numbers. Again, if you think of this process, again, the wavy line represents a reggeon, in this particular case, Pomeron. So if you just focus on the top plot of the top part of these diagrams, you can think of that as essentially a quasi two-body process in which the region that represents a particle interacts with the pi minus and scatters into eta pi. So what you see here on the top left is a scattered plot, mass of the eta pi versus the scattering angle between the pi minus and the eta in the rest frame of pi 1, and a similar process for GluX, where the beam is now replaced, the pi beam is now replaced by a photon. And also in the case of the GluX, there is also data on the charge exchange, as I said. What you see here on this, I'm going to focus on what we refer to as the compass plot, which is the scattered plot on the left. And what you see here is of course at the lower mass, you see this prominent double hump structure, which is essentially dominated by production of the A2 meson here. This is the projection of the data on the eta pi mass. But then the distribution definitely changes shape. Instead of being essentially vertical bands at fixed eta pi mass, you see these sort of wings either in the forward eta or the forward pion direction. So this change in the event distribution definitely indicates the change in the production process. So here you have eta pi versus eta pi prime distributions. You see essentially the eta pi is largely symmetric in this shaded region within the red box. The eta prime is more asymmetric, and that's reflected in the distribution of events here projected on the eta prime pi mass. So this is the p wave actually extracted. So the p wave, as I said, corresponds to the asymmetry in the angular distribution between eta and the pi. So in this lower mass range, you're expecting that indeed that this presence of bands at fixed mass corresponds to direct production of resonances, a single region exchange. And as one goes to this wing area, then this can be easily interpreted in terms of the double Regge exchange process. So the forward eta corresponds to exchange of A2 region trajectories, and the backward region correspond to exchange of isoscalars, either F or the Pomeranian trajectory. So the existence of asymmetry, which in the lower mass translates into existence of exotic P wave, essentially is reflected into a difference between properties of the isovector A exchange and properties of the isoscalar F exchange, and also existence of the Pomeranian exchange. So clearly one would indeed expect that the production of the eta prime pi has indeed a larger asymmetry, because eta prime phenomenologically is expected to have a much larger gluon content, and therefore larger coupling to isoscalar exchanges, including the Pomeranian. So,
excuse me, 5 minutes.
Yes, thank you. So what we have done is basically taking the compass data. Compass has analyzed this event distribution using partial wave expansion, and the partial wave expansion that they've used is beyond this resonance region, covers this blue region that I'm showing here. So we've reconstructed the sort of the wings from the partial waves, and then analyzed these distribution in terms of various collections of various types of exchanges, as I said, including the isovectors and isoscalars. And here you see, now, by the way, this paper appeared on arXiv just today. So you see the comparison between the data, which is shown in this shaded region, including the uncertainties in the data, and then fits to the data for various assumptions about which diagrams dominate. And here, what I'm showing here, the blue arrow here indicates the relationship between the top A2 versus top F2 exchange. Again, in the SU3 limit, and ignoring the Pomeranian exchange, these should be the same. And you indeed see that the data does say that there is basically the large degeneracy between A and F exchange in the case of the eta production. So again, these two, the blue and red, approximately similar couplings, but there is nevertheless some difference. And of course, that difference leads to asymmetry, this forward-backward asymmetry. And that difference appears to be much larger in the case of the eta prime production, where the A2 and F2 have quite different couplings to the eta prime. And that again reflects in a much larger asymmetry in the case of the eta prime. So this is the forward and backward intensity, basically number of events integrated in this forward and backward wings, and you see how it compares with sort of the theoretical prediction based on Regge exchanges, the total intensity, and finally here's the forward backward asymmetry, which, as I said, essentially is explained because of the difference between how the isoscalar and isovector trajectory is coupled to the eta, and also significant contribution of the Pomeron exchange in the case of eta prime. So some time ago, we also looked into the resonance region and extracted actually the Paul parameters of an exotic meson using the same partial wave data set, but now, as I said, the lower mass. So this is the comparison of our amplitude analysis with the compass data, and what that amplitude analysis gave us is essentially a single exotic somewhere in between the 1400 and the 1600, which is listed in the PDG, but now we claim that it's really only one, and the difference between its mass position, as you can see here from the left plot, has to do essentially with the kinematics. So the single resonance peaks of the lower mass when measured using eta pi decay versus a higher mass when measured using eta prime pi. So this has already been taken into account by PDG. This is a comparison with recent lattice calculations. So what Lattice did, they calculate the exotic meson, the hybrid meson pole position using the SU3 symmetry limit, and then use our mass to extrapolate to the couplings and therefore predict the widths of how, and partial widths of how the exotic will couple to these golden channels, the golden channels in particular, the eta prime and eta prime pi, indicating indeed the large difference between the two. So ultimately, what one needs to do is basically connect this wing region with the resonance region, and this is done using finite unit sum rules. This is work in progress, but just to illustrate here, this is what we've done for the single meson production, where essentially one compares partial wave analyses, either from SAT or from MADE, to describe the amplitude in the resonance region with expectation from the Regge exchanges in the higher mass region, and essentially finds a full agreement, and actually one can find some discrepancies that eventually will take into account by subsequent MADE analysis that we're able to explain why there's a difference between the high energy prediction and the lower mass, original lower mass fit. So I'm going to skip XYZs and just summarize the existence of hadrons and hybrids in particular are certainly consequence of gluon dynamics. So understanding better the spectrum will definitely teach us more about mechanisms for mass generation and confinement. The XYZ phenomena are very intriguing. There may be molecules, compact states, and I think looking at their properties in the context of reggelons will also teach us more about the connection to QCD and more complicated phenomena. So thank you.
Thank you, Adam, for a very nice talk. Questions? So if anybody has questions or comments, please raise your hand. So it seems the talk is very clear. So I have a question actually for the pi 1. Is it possible that, for instance, channels like B1 pi or F1 pi, this kind of stuff, play a role there?
Yeah.
B1 pi. B1 pi.
Well, you see here already, B1 pi is
okay.
It's always been expected to be the largest. I mean, if you go back to our old calculations in the so-called 3P0 model, that would, for example, predict that hybrids would primarily decay into P-wave and S-wave mesons. And that was originally postulated to be the case, assuming that the gluons essentially behave like excited flux tube. but it turned out to be pretty robust using other microscopic models for what the constituents of hybrid are. You often find these P plus S wave mesons to dominate the decays. So of course the problem with this is a very complicated final state to reconstruct, because B decays to omega pi, omega decays to 3 pi, so you're counting 5 pi's in the final state.
That's right.
But that's what GluX is ultimately gearing up to determine as well.
If this channel is really important, then would one have a kind of picture that this pi 1 is something like molecular stuff?
As I said, I mean, the models in which the pi 1 is a compact state would predict this large number. So I don't know
Okay.
I don't know what models, molecular type models would give. I'm not aware of any calculation like that. That's certainly something that would be interesting to look at.
Yeah, thank you. So then let's thank all the speakers in this session, and we reconvene at in 20 minutes, in 22 minutes. Yes, thank you.